All right, today we are going to talk about polar graphs and polar coordinates. And so we want to first start out by trying to figure out how to sketch polar coordinates. And so what we realize here is that all polar coordinates are written in the form r comma theta. And r is the distance away from the origin, and theta is the angle that you go towards on the unit circle. So letter A, 4 comma 2 pi over 3, means to go 4 units in the direction of 2 pi over 3. 2 pi over 3 is equal to 120 degrees. And so on the polar paper, we will go 4 units in the direction of 120. So here's our origin, and we will go 1, 2, 3, 4 units, and we'll put a point right there. All right, and the next one is 3 units in the direction of 7 pi over 6. 7 pi over 6 is 210 degrees. And so we are going to go 3 units in the direction of 210. And so that's going to be 1, 2, 3. It's pretty simple stuff. And then we're going to go for letter C. This negative right here means simply to go 2 units in the opposite direction. So you're going to want to probably write that down. Opposite direction of 5 pi over 4. 5 pi over 4 is 225. So if we go in the opposite direction, we're going to be, instead of quadrant 3, we're going to be in quadrant 1. And we're going to go 2 units in the direction of 45. So that's going to be 1 and 2. So that's going to be that point right there. And then the last one is going to be 2 units in the direction of negative 30 degrees. That just simply means we want to rotate clockwise 30 degrees, which puts us over here at 330. We're going to go 2 units in the direction of that angle, and that's going to put us right there. And so that is how you graph polar coordinates. All right, let's say you have a triangle, and we see that, let's say we'll call this side of the triangle x, we'll call that side y, and we'll call the hypotenuse r, and we'll call this theta. So if we do the Pythagorean theorem, we see that x squared plus y squared equals r squared. And so the first relationship that we want to develop as we are converting from rectangular coordinates to polar coordinates, and by the way, let me review that. Rectangular coordinates are x, y, over some x right and left and up and down some y value. Polar coordinates are r and theta, and so we're going to have to convert back and forth. The second thing we see is we can say, let's say we have sine of theta, and we know that's going to be the opposite side over your hypotenuse, and cosine of theta is going to be your adjacent side over your hypotenuse. So now we see that relationships 2 and 3 are going to be that y is going to equal r sine of theta, and x is going to equal r cosine of theta. And so from now on, we can use these 3 relationships as we are converting back and forth from rectangular to polar and vice versa. So suppose we want to convert letter A, which is y equals 4, and this is in rectangular form because we see x's and y's. In this case, just a y. We want to convert that to polar. So we are going to make a substitution. We're going to let y equal r sine of theta, and we're going to solve it for r. So r sine of theta equals 4. We're going to divide by sine of theta, and we get r equals 4 cosecant of theta. And what does that mean? Well, we know that y equals 4 is nothing more than just a horizontal line. And so if our calculator was in polar mode and we wanted to graph a horizontal line, we would type in 4 cosecant of theta, and that would give us a horizontal line. All right, so for letter B, we see that this is a circle centered at 0, 0 with a radius of 5. And so we want to take that and convert it from rectangular coordinates into polar coordinates. And so we're going to make some substitutions. We're going to let x equal r cosine of theta. So we will say r cosine of theta squared plus r sine of theta for the y squared equals 25. All right, when we square that, we get r squared cosine squared of theta plus r squared sine squared of theta equals 25. We can factor out an r squared, and we remember from trigonometry that this is the most basic Pythagorean identity. Cosine squared plus sine squared equals 1. So we end up getting r squared equals 25, or r equals 5, and we take the square root of both sides. So what does this mean? It means if we wanted to graph just a basic circle centered at 0, 0 with a radius of 5, and we were in polar mode in our calculator, we would just type in r equals 5, and that would give it to us. All right, so now we want to go backwards. We are given equations that are in polar form. We know that because there is an r and there is a theta, and we want to go backwards and go to rectangular form. So this one's a pretty simple one. We can look at this and say y is equal to r sine theta. So wherever we see r sine theta, we can replace it for y. So y equals 3. And if we were asked to sketch a graph of this, we know that this would simply just be a horizontal line at y equals 3. So that one is pretty much done. And so now we are on letter B. R is equal to 2 cosine of theta. And so what we want to do here is we want to recognize that, you know what, somewhere along the way I want to use the fact that x is equal to r cosine theta. But we don't have an r cosine theta. But what we can do is we can multiply both sides by r in this equation, and that is going to create r squared equals 2r cosine theta. So now we remember that r squared is equal to x squared plus y squared, and that gets us into rectangular form, so x squared plus y squared. And then we can realize that r cosine theta, so this piece right here, we can replace that with x. So it's going to be 2x. All right, now we're going to move the 2x over to the other side, and we're going to complete the square, and we're going to see what type of shape this makes. So let's review completing the square. You are going to take half of the middle term, so half of negative 2, which is negative 1, and square that. So that's going to give you a positive 1. And you have to balance your equation by putting a positive 1 over here. So we added a 1 on this side. We need to add a 1 on the other side. And so this is simply going to be plus y squared. And then this factors into x minus 1, x minus 1, which we can write as x minus 1 squared plus y squared equals 1. And so now we can recognize that as a circle with a center of 1, 0, and a radius of 1. So if we sketched it, that's what it would look like. Now this third one, actually, it may not be so apparent what type of graph it is or what equation it makes, but it just says theta is equal to 2 pi over 3. So if we recognize that 2 pi over 3 is the same as 120 degrees, then we can draw, let's just say we draw a line right there, and that's going to be 120 degrees. So if we make a triangle here, we will remember that the coordinates of 120, the x and y, well, let's just kind of look at it. 120 degrees means that it's going to be 60 degrees rotated north of the x-axis. And so we know that in these 30, 60, 90 degree triangles, root 3 is going to be opposite of 60, and 1 is going to be opposite of 30, but we're going left, so you got to make it negative, and then the hypotenuse is 2. All right, so if we want to find the slope of this line, we can see that the line is clearly going through the origin. So the line is going to be y equals, and now we just need to know the slope. Well, slope is rise over run. So rise is our root 3, and our run is negative 1. So, and then we need an x, okay, because the equation has to be y equals some slope times x if it goes through the origin. So your answer here is y equals negative root 3x. And that is the answer. All right, in this example, we're asked to find dy dx of the polar function r equals 3 plus 2 sine theta at the given point theta equals pi over 6. So let's just say, for example, that this graph, we'll look at later what these graphs look like. Let's just say, for example, that that's what the graph looks like. And let's say that we are wanting to find the slope of this curve at the point at the angle pi over 6, which is 30. So we're asked to find the slope of that tangent line. That's basically what we're trying to do here, is find the slope of that line. So dy dx we can see is equal to dy d theta over dx d theta. This is true because when you divide fractions, you're going to flip the second one and you're going to multiply. So it's going to be d theta over dx, and the d thetas cancel, so you get dy dx. All right, so we're going to apply that to this problem. And so what we first need to do is we need to come up with expressions for y and x. So we remember that y is equal to r sine theta. Well, r is given to us. It's 3 plus 2 sine of theta times, and this is the part that you have to be careful with, times sine of theta. So this is your r, and this is your sine theta right here. All right, so x is going to be r cosine theta. So r, once again, is 3 plus 2 sine of theta cosine of theta. And so here's where you have to be careful, because this is going to be your r, and this is going to be your cosine theta right here. And so now if we want to find dy dx, we need to do first dy d theta. So we're going to take the derivative of y with respect to theta, which just means we're going to have to use the product rule. So it's going to be the first, which is 3 plus 2 sine of theta, times the derivative of the second, which is cosine theta. By the way, I'm taking the derivative of this right here, product rule, plus the second, which is sine theta, times the derivative of the first, which is going to be 2 cosine of theta, because the 3 goes away. So I'm going to put the 2 right here and put the cosine of theta right there. And all of this is divided by dx d theta. So we need to do the same thing with this equation, product rule. So it's going to be the first, 3 plus 2 sine of theta, times the derivative of the second. The derivative of cosine is just negative sine, plus the second, which is cosine of theta, times the derivative of the first, which is going to be 2 cosine theta. And that's going to turn that into 2 cosine squared of theta. And now at this point, we basically just, and this is our dy dx. And so now we just need to plug in, well, our angle's 30 degrees, so we remember our sine of 30 is 1/2. And our cosine of 30 is going to be root 3 over 2. So to save time, you plug in all of those answers there, and you will end up getting an answer of negative 5 root 3. And so that would be the slope of the line at that point. All right, so now in this example, we want to learn how to find the area between a polar curve and an axis. So for this example, we have the polar function r is equal to 2 plus 2 sine of theta. So we want to sketch that, and then we want to find the area as well. So in order to sketch these, the best thing to do is just make a basic table, and maybe we'll put theta here and r there, and you're just going to want to pick the most basic angles on the unit circle. So the 0, 90, we should probably use radians. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. And we want to see what the radius would be. So we're going to plug in these values into our function. So when we plug in 0 in for theta, well, we know that sine of 0 is 0, times 2 is 0, plus 2, so our radius is 2. Pi over 2 is 90, so we plug 90 in here. right here, sine of 90 is 1 times 2. 2 plus 2 is 4. And then pi is 180. That's going to be 0. Sine of 180 is 0, so that's going to be 2. 3 pi over 2 is going to be 270. That's going to give us a negative 1 as its sine value, times 2 is negative 2. 2 plus negative 2 is 0. 2 pi is going to be the same as 0, so that's just going to be 2. So if we were to graph this, what we would do is we would say, okay, I'm going to go in the direction of 0 degrees 2 units. So I'm going to go 0 degrees on the unit circle is over there. And then I'm going to go 4 units in the direction of pi over 2. So I'm going to put another point there. Then I'm going to go 2 units in the direction of pi. So that's 2 in the direction of 180. And then 0 units in the direction of 3 pi over 2. So that means you're not going anywhere. You're going to be at the origin. All right, and then 2 units in the direction of 2 pi. So this thing is going to look like this. And then it's going to come around looking like that. It's probably not the best sketch. But what we are interested in finding is all of this area right here. And so in order to do that, we're going to use this formula that we've been given. Area is equal to 1/2 the angle alpha to the second angle beta r squared d theta. Now, I want to make sure you understand something. For a lot of these problems, you can use symmetry. You can use symmetry. In other words, we can see that this has perfect symmetry, as do the graphs that we're going to be looking at. So really, you can just find the area of one side or the other and then double it. But for this purpose, for this example, we're just going to use the basic example that we've been, or excuse me, the basic equation that we've been given. So area is equal to 1/2, and we're going to integrate from 0 to 2 pi of r squared, and r is going to be 2 plus 2 sine of theta all squared d theta. So when we FOIL this out, and please don't raise 2 to the squared and 2 sine theta, you actually have to FOIL this out. So it's going to be 4 plus 4 sine squared theta plus 4, actually 8, excuse me. So that's going to be 8 sine of theta. We can factor out a 4 from each one of these terms here. This is a 4, this is a 4, this is a 4. We can factor out a 4 and put it in front, and that's going to multiply to the 1/2 and make it 2. So it's going to be 2 integral from 0 to 2 pi of 1 plus, I'm just going to move this sine theta in front here. It's going to be 2 sine of theta plus sine squared of theta, d theta. Now, for integrating this, 1 is going to be pretty easy, and integrating 2 sine theta is going to be pretty easy. But sine squared does not have an antiderivative. So you may remember this a little while ago. We need to say that sine squared theta is equal to 1 minus the cosine of 2 theta over 2. And that is a double angle formula for the sine squared. And so we're going to integrate 1, and we're going to get theta. We're going to integrate 2 sine of theta, and that's going to give us negative 2 cosine of theta. And then we're going to replace sine squared with 1 minus cosine of 2 theta over 2. And we can split this up into 2 integrals, 1/2 minus cosine of 2 theta over 2. And we're going to integrate 1/2, and that's going to give us 1/2 theta. And then we're going to integrate negative cosine 2 theta over 2. So we remember that the derivative of cosine is negative sine, so the integral of cosine must be positive sine, but there's a negative in front, so it's going to be negative sine of 2 theta. And it would be over 2, but we've got to divide by 2 right there, so it's going to end up being over 4. So you plug in all of your values for your upper and lower limits, and you end up getting 6 pi. I'm going to save time on this video and just give you the answer there. All right, for this example, it is helpful to know what the basic shape of some of these polar graphs are. Here, we're just going to have a little flower type of shape here. This number here is the radius of the petals, and this number here, if it's even, you're going to double it, and that's going to tell you how many petals there are. And so you can kind of sketch this on your calculator if you want. We're going to see that, so we're going to have each petal is going to have a length of 4. And that's determined by the coefficient in front. And so it's going to look like this. Come around here and go up there. And there is the basic shape of this polar graph. It says, set up the integral, do not evaluate, to find the area of just one of these petals. All right, just one of the petals. So I'm going to choose this one here. It doesn't really matter which one you choose. Now, I want you to notice something. Each petal starts and stops, let me just go through it, at the origin. Each petal starts and stops at the origin. Well, we know at the origin, the r is equal to 0. You're not going anywhere. The radius is 0 at the origin. So what you want to do is that you want to set this equation for cosine of 2 theta, which is equal to r. You want to set that equal to 0, and you're going to find the angles where the radius is equal to 0. So we'll divide by 4, and we get cosine of 2 theta is equal to 0. Now we just have to basically ask the question, so why don't we do this? Matter of fact, why don't we just temporarily let u equal 2 theta. Now we're not going to do u substitution as far as derivatives or anything, but we're just going to say cosine of u equals 0. So the question is, where is the cosine equal to 0? Well, the cosine is your x coordinate, so that would be 0 at pi over 2 and 3 pi over 2. So pi over 2, 3 pi over 2. So u is going to be pi over 2, and when u is 3 pi over 2. But we're interested in theta, so we're going to plug this 2 theta in for u. So 2 theta. So we see that when theta is pi over 4, and when theta is 3 pi over 4, the radius is equal to 0. So that gives us the limits of integration for this problem for the area of one of these petals. So we'll say the area is equal to the integral from pi over 4 to 3 pi over 4 r squared, and r was given to us 4 cosine of 2 theta squared d theta, and that's all we have to do for this problem is set it up. All right, it says find the area of the inner loop of r equals 1 plus 2 sine theta and use your calculator to evaluate. So why don't we set up a table once again and see what this graph looks like. So we'll have theta here and r there, so we'll have 0, pi over 2, pi, 3 pi over 2, and 2 pi going to be our angles. So we plug in 0, and I'm just going to give these answers to you. You're going to get 1, and when you plug in pi over 2, you're going to get 3. When you plug in pi, you're going to get 1. When you plug in 3 pi over 2, you're going to get -1. And then 2 pi is always the same as 0, so you're going to get 1. So let's see if we can figure out what this graph will look like. It is going to look something like this. When 0 degrees, we're going to go 1 unit to the right and put a point. Pi over 2, we're going to go 3 units up and put a point. And 1 unit in the direction of 180, so we're going to put a point. And now watch this now, right here. 1 unit in the opposite direction of 3 pi over 2. Well, 3 pi over 2 is 270, but we're going 1 unit in the opposite direction, so that's towards 90. All right, so, and then 2 pi, we're back to 1. So this thing actually looks like this. It's coming around, and it's going to go through the origin, go up there, come through the origin again, and then go back. And so what they're asking us for is the area of the inner petal. All right, that inner loop right there. Excuse me, not a petal, inner loop. So once again, we've got to figure out where the radius is 0, because that's going to be where the inner loop starts and stops. So we're going to set this equation 1 plus 2 sine theta equal to 0. So sine of theta is equal to -1/2. So when we think about the unit circle, that's our opposite over hypotenuse. Opposite over our hypotenuse. And so we know that in a 30, 60, 90 degree triangle, the 1 is always across from 30. So that's going to be 30. That's going to be 30. So our angles are going to be 210 and 330, which in radians is going to be 7 pi over 6 and 11 pi over 6. So we're going to integrate using our area formula 1/2 7 pi over 6 to 11 pi over 6 r, which is 1 plus 2 sine of theta squared d theta. And we plug this into our calculator, we get 0.544 as a final answer.